Hello and welcome. In this video, we will be exploring the fundamental concept of limits in calculus. This topic is a cornerstone of the IB Mathematics Analysis and Approaches higher level curriculum. By the end of this session, you will be able to define a limit, evaluate limits using algebraic techniques and limit laws, understand the conditions for a limit to exist, and finally, define and identify continuity in functions. Let's begin with an intuitive idea of what a limit is. Imagine a sequence of numbers that gets closer and closer to a specific value. Consider the sequence 0.3, 0.33, 0.333, and so on. This sequence can be defined by the general term x sub n equals 0.3 repeating n times. As we take more and more terms in this sequence, the numbers get closer and closer to a specific fraction. That fraction is 1/3. We can say that the limit of this sequence, as n approaches infinity, is 1/3. This is written as the limit as n tends to infinity of x sub n equals 1/3. This idea of approaching a value is central to the concept of a limit. It's about the behavior of a function as its input gets arbitrarily close to a certain point. Now let's formalize this idea for functions. Our goal in this scene is to define a limit and learn how to evaluate it algebraically. The informal definition of a limit states that if a function f of x gets arbitrarily close to a real number L as x gets arbitrarily close to a number a, then we say the limit of f of x as x approaches a is L. We write this as the limit as x approaches a of f of x equals L. It's crucial to note that the limit is about the behavior of the function 10 to near times a, not 10 to time a. The function doesn't even need to be defined at x equals a for the limit to exist. Let's look at an example. Consider the function f of x equals the quantity 5x plus x squared, all divided by x. We want to find the limit as x approaches 0. If we try to substitute x equals 0 directly, we get 0 over 0, which is an indeterminate form. This tells us we need to do more work. Instead, let's simplify the function. We can factor out an x from the numerator, giving us x times the quantity 5 plus x, all over x. Since we are considering the limit as x approaches 0, we are looking at values of x that are very close to 0, but not equal to 0. Therefore, we can cancel the x in the numerator and denominator. So, for all values of x except 0, our function behaves exactly like the line y equals x plus 5. Graphically, this is the line y equals x plus 5, but with a hole at the point 0, 5. This hole is a point of discontinuity. However, the limit still exists. As x approaches 0 from either side, the function's value approaches 5. Therefore, we can conclude that the limit as x approaches 0 of our original function is 5. This example clearly shows that the limit is about the trend of the function, not its value at the point. To evaluate limits more systematically, we can use a set of rules called the limit laws. In this scene, we will review these laws and apply them to solve problems. Let's assume we have two functions, f of x and g of x, and we know their limits as x approaches a are L and m respectively. That is, the limit of f of x is L, and the limit of g of x is m. The first law is the sum and difference law. The limit of a sum or difference of functions is the sum or difference of their individual limits. So, the limit of f plus or minus g is L plus or minus m. Next is the product law. The limit of a product of functions is the product of their limits. The limit of f times g is L times m. And finally, the quotient law. The limit of a quotient of functions is the quotient of their limits, provided the limit of the denominator is not 0. The limit of f over g is L over m, as long as m is not 0. These laws allow us to break down complex limits into simpler ones. Let's see them in action with a few examples. First, let's evaluate the limit as x approaches 2 of x squared. Using the product law, this is the limit of x times the limit of x, which is 2 times 2, or 4. Next, let's evaluate the limit as x approaches 3 of the quantity x squared minus 9, all over x minus 3. If we substitute x equals 3, we get 0 over 0. So we must simplify. We can factor the numerator as a difference of squares, giving us x plus 3 times x minus 3. Since x is approaching 3 but is not equal to 3, x minus 3 is not 0, and we can cancel it. This leaves us with the limit of x plus 3 as x approaches 3, which is 3 plus 3, or 6. These examples demonstrate how algebraic manipulation, combined with the limit laws, is a powerful tool for evaluating limits, especially when direct substitution leads to an indeterminate form. In this scene, we will explore the conditions under which a limit exists. Our objective is to understand one-sided limits and the formal criterion for a two-sided limit. So far, we've considered the limit as x approaches a from both sides. We can also define one-sided limits. The limit as x approaches a from the left is written with a superscript minus, and the limit as x approaches a from the right is written with a superscript plus. The formal condition for a two-sided limit to exist is that the left-hand limit and the right-hand limit must both exist and be equal to the same finite value, a. If this condition is met, we say the function converges to a. If the one-sided limits are not equal, or if one or both of them do not exist, then the two-sided limit does not exist. Let's look at some examples of when a limit fails to exist. Consider this piecewise function. As x approaches 1 from the left, the function's value is 4, so the left-hand limit is 4. As x approaches 1 from the right, the function's value is 2. The right-hand limit is 2. Since the left and right limits are not equal, the two-sided limit as x approaches 1 does not exist. This is a discontinuity. Now consider the function f of x equals 1 over x squared. As x approaches 0 from either the left or the right, the function's value increases without bound, tending towards positive infinity. Because the function does not approach a finite value, the limit does not exist. This is a break discontinuity or an infinite discontinuity. It's important to remember that infinity is not a number, so if a limit is infinite, we say it does not exist. Understanding these conditions is key to analyzing the behavior of functions. In this scene, we will investigate the behavior of functions as x becomes infinitely large or infinitely small. Our objective is to evaluate limits at infinity, which are crucial for finding horizontal asymptotes. We write x tends to infinity to mean x increases without bound, and x tends to minus infinity to mean x decreases without bound. The key idea here is to consider the term 1 over x to the power of n. As x gets very large, the value of 1 over x to the power of n gets very, very small, approaching 0. This is true for any positive power n. This fundamental result is the basis for evaluating many limits at infinity. Let's apply this to rational functions, which are fractions of polynomials. The strategy is to divide every term in the numerator and denominator by the highest power of x in the denominator. Consider the limit as x approaches infinity of the quantity 2x plus 3, all over x minus 4. The highest power of x in the denominator is x to the power of 1. So we divide every term by x. This gives us the limit of 2 plus 3 over x, all over 1 minus 4 over x. Now, as x approaches infinity, the terms 3 over x and 4 over x both approach 0. So the limit simplifies to 2 over 1, which is 2. This result, 2, is the horizontal asymptote of the function. The function approaches the line y equals 2 as x gets very large. Let's try another one. Evaluate the limit as x approaches infinity of x squared plus x plus 1, all over x minus 2. The highest power of x in the denominator is x to the power of 1. So we divide by x. This gives us the limit of x plus 1 over x, all over 1 minus 2 over x. As x approaches infinity, the numerator approaches infinity, while the denominator approaches 1. An infinitely large number divided by 1 is still infinitely large. Therefore, the limit does not exist. This means the function has no horizontal asymptote. Instead, it grows without bound, indicating a slant asymptote. In this scene, we will focus on a very important trigonometric limit. Our objective is to understand and apply the limit as theta approaches 0 of sine theta over theta. This limit is a fundamental result in calculus. It states that the limit as theta approaches 0 of sine theta over theta is equal to 1, provided theta is measured in radians. Let's visualize this. If you graph the function y equals sine x over x, you'll see that as x gets closer and closer to 0, the graph approaches the value 1. There's a hole at x equals 0, but the limit exists. This limit is often proven using the squeeze theorem, which involves comparing the area of a sector of a circle to the areas of two triangles. The key is that for small angles, sine theta is very close to theta. Now, let's see how to use this limit to solve problems. The strategy is to manipulate the expression to match the form sine of something over the same something. Consider the limit as theta approaches 0 of sine of 3 theta over theta. We want the denominator to be 3 theta. We can achieve this by multiplying the numerator and denominator by 3. This gives us the limit of sine of 3 theta over 3 theta, all times 3. We can pull the constant 3 out of the limit. Now, as theta approaches 0, 3 theta also approaches 0. So the limit of sine of 3 theta over 3 theta is 1. The final answer is 3 times 1, which is 3. Let's try another one. Find the limit as theta approaches 0 of 2 theta over sine of 3 theta. This is a bit different, but we can use the same principle. We can rewrite this as the limit of 2 over 3 times the quantity 3 theta over sine of 3 theta. We know that the limit of sine of x over x is 1. The limit of x over sine of x is also 1. So the limit of 3 theta over sine of 3 theta is 1. The final answer is 2 over 3 times 1, which is 2 over 3. Mastering this trigonometric limit and the technique of algebraic manipulation is essential for success in IBAHL calculus. Our final topic is continuity. In this scene, we will define continuity at a point and classify different types of discontinuities. A function f is continuous at a point x equals a if 3 conditions are met. First, the function must be defined at a. Second, the limit of the function as x approaches a must exist. And third, the value of the function at a must be equal to the limit. Intuitively, a function is continuous if you can draw its graph without lifting your pen. If any of these 3 conditions fail, the function is discontinuous at that point. There are 2 main types of discontinuities. A removable discontinuity occurs when the limit exists, but it's not equal to the function's value, or the function is undefined. This is often a hole in the graph. An essential discontinuity occurs when the limit does not exist, such as a jump or a break vertical asymptote. Let's look at an example of a removable discontinuity. Consider the function f of x equals x squared for x not equal to 2, and f of x equals 6 for x equals 2. Let's check the 3 conditions for continuity at x equals 2. First, f of 2 is defined and equals 6. Second, the limit as x approaches 2 of f of x is the limit of x squared, which is 4. Third, the limit, 4, is not equal to the function's value, 6. Since the third condition fails, the function is discontinuous at x equals 2. Because the limit exists, this is a removable discontinuity. We can remove it by redefining the function at x equals 2. If we define a new function g of x to be x squared for all x, then g of 2 is 4, which is equal to the limit. This new function g is continuous everywhere. This process of redefining a function to make it continuous is a key concept in HL calculus. Let's work through a more complex example that combines several of the concepts we've learned. This is a typical IB style problem. Consider the function f of x equals the square root of x squared plus x minus x. We want to find the limit as x approaches infinity. If we try to substitute infinity, we get infinity minus infinity, which is another indeterminate form. We need an algebraic trick to simplify this. The trick is to multiply the expression by its conjugate. The conjugate of the square root of x squared plus x minus x is the square root of x squared plus x plus x. We multiply both the numerator and the denominator by this conjugate. This is of the form a plus b, which simplifies to a squared minus b squared. In our case, a is the square root term and b is x. So the numerator becomes x squared plus x minus x squared. The x squared terms cancel out, leaving just x in the numerator. Our limit now looks like this. The limit as x approaches infinity of x, divided by the square root of x squared plus x plus x. This is still an indeterminate form, infinity over infinity, but it's in a form we can handle. Now we use the technique for limits at infinity. We divide every term by the highest power of x in the denominator. the highest power is x to the power of 1. Dividing the numerator by x gives 1. In the denominator, we divide the x outside the square root by x to get 1. For the term inside the square root, we divide by x squared, which is the same as dividing by x outside the square root. This gives us the square root of 1 plus 1 over x. Now, as x approaches infinity, the term 1 over x approaches 0, so the expression simplifies to 1 over the square root of 1 plus 0 plus 1. This is 1 over 1 plus 1, which equals 1 over 2. The limit is 1/2. This problem demonstrates the importance of algebraic manipulation and combining different limit techniques. It's a great example of the level of rigor expected in IBAAHL. Let's conclude with a quick recap of the key concepts we've covered. We started with the informal definition of a limit, which describes the value a function approaches as its input gets close to a certain point. We then learned the limit laws for sums, products, and quotients, which allow us to evaluate limits algebraically. We saw that a limit exists only if the left-hand and right-hand limits are equal. This led us to the concept of continuity, where a function is continuous at a point if it's defined there, the limit exists, and the two are equal. We also explored limits at infinity to find horizontal asymptotes, and we learned the fundamental trigonometric limit, sine theta over theta equals 1, which is essential for many problems. These concepts are the building blocks for the rest of your calculus journey. Thank you for watching. To solidify your understanding, here are 5 practice questions designed to reflect the style and difficulty of IBAAHL assessments. Pause the video, work through them, and then resume to see the fully worked solutions. Here are the questions. Question 1 involves a piecewise function and continuity. Question 2 is a limit at infinity. Question 3 is a trigonometric limit. Question 4 is a limit involving a square root, similar to our last example. And question 5 asks you to find a constant to make a function continuous. Take your time to solve these. When you're ready, let's go through the solutions. Welcome back. Let's review the solutions to the practice questions. For question 1, we need to check the 3 conditions for continuity at x equals 2. First, f of 2 is defined as 3. Second, we find the one-sided limits. The left-hand limit is 3, and the right-hand limit is 5. Since the left and right limits are not equal, the two-sided limit does not exist. Therefore, the function is discontinuous at x equals 2. This is an essential discontinuity, specifically a jump. For question 2, we have a limit at infinity. We divide every term by x squared, the highest power in the denominator. This gives us the limit of 3 minus 2 over x plus 1 over x squared all over 1 plus 5 over x minus 4 over x squared. As x approaches infinity, all the terms with x in the denominator go to 0. The limit is 3 over 1, which is 3. For question 3, we have a trigonometric limit. We multiply the numerator and denominator by the conjugate of the numerator, which is 1 plus cosine theta. This simplifies the numerator to sine squared theta. We can then split the expression into sine theta over theta times sine theta over theta times 1 over 1 plus cosine theta. The first 2 terms go to 1, and the third term goes to 1 over 2. The final answer is 1/2. For question 4, we use the conjugate trick again. Multiplying by the conjugate gives us 3x in the numerator. Dividing by x, the highest power in the denominator, gives us 3 over the square root of 1 plus 3 over x plus 1. As x approaches infinity, the term 3 over x goes to 0, and the limit is 3 over 2. For question 5, for the function to be continuous, the 2 pieces must meet at x equals 1. This means the left-hand limit must equal the right-hand limit. Setting the 2 expressions equal at x equals 1 gives us k plus 2 equals 3 minus k. Solving for k, we find that k must be 1/2. I hope these examples and practice questions have helped you deepen your understanding of limits and continuity. Keep practicing, and you'll master these essential calculus concepts.